This is where we left off with our introduction to passive elements, so I'm just going to review this slide and then we'll move on to the new material. So if we're adding up resistors in series, like we see on the left side here, we know from Kirchhoff's current law that the voltage or the current that flows through resistor 1 also has to flow through resistor 2, because as it comes through, it gets to this node and it has to exit somewhere, and the only place available for it to exit is through resistor 2. So we know that I1, the current through resistor 1, is equal to I2. So the rest of the derivation, I'm just going to call that I, because we know that that's the overall current through the circuit. So using Kirchhoff's voltage law, we know that the voltage drop across the overall circuit, so V to ground, has to equal the sum of the voltage drop across resistor 1 plus the voltage drop across resistor 2. So we can see that in this equation up here, where we've already replaced the voltage of resistor 1 and 2 with the Ohm's law form of it. So the voltage drop across the overall circuit equals the voltage drop across resistor 1, which is just I times R1, plus the voltage drop across resistor 2, I times R2. So if we pull out the I from each of those terms and group the R's together, we see this notation. So we have, this looks a lot like Ohm's law, where we have a voltage equal to a current times a resistance. So if we treated the overall resistor network, so the two resistors in series, as a single resistor, that resistor would have a resistance of R1 plus R2, and we call that the equivalent resistance of the circuit. So that is equal to R EQ. So if we do the same thing for some resistors in parallel, we can follow the same logic to get the equivalent resistance. So we know that the overall current coming from the voltage source gets into this node, and then it has to split between the two resistors. So the overall current is equal to the current through resistor 1 plus the current through resistor 2. And we know the current through resistor 1 is equal to the voltage drop across it divided by its resistance. So same thing holds for resistor 2. So that's how we get this equation where the current is equal to the voltage across the whole circuit divided by resistance 1 plus that voltage divided by resistor 2. Now that we have this equation, we want to get back to that equivalent resistance, so we need to group terms together. So we get a common denominator for everything, and then we pull out the voltage and add the resistor values together, and we get this format. But we want it in that Ohm's law format, where we have the voltage equal to a current times some resistances. To do that, we'll divide both sides by this resistor group, and that gives us this format. So here we can see the equivalent resistance of the resistors in parallel is just equal to the product divided by the sum. So one thing to note is for resistors in parallel, the overall resistance is going to be less than any of the resistors in the circuit, where when we're adding resistors in series, the overall resistance is going to be greater than any of the resistors in the circuit. And if we think about physically what's going on here, if we go back to how we get resistance, resistance for an item is equal to its resistivity times its length divided by its area. So if we have resistors in series, it's like we're adding length to a resistor. So this is, if we go back to the water analogy, if we had a really long pipe, if we increase the length of that pipe, it's going to make it harder to push water through because we're increasing the length. Similarly, for resistors in parallel, it's like we're increasing the area. So if we have two straws we're blowing through, it's going to be easier than blowing through a single straw because the area is similar to the area of two straws. Now we can do the same thing with capacitors as well. So if we have capacitors in parallel, following the same logic, we start out with Kirchhoff's current law, where the voltage through the overall circuit is equal to the sum of the current through each of the branches. So in this case, the current through a capacitor is equal to its capacitance times the change in voltage. So we get this top equation where the overall current is equal to capacitance 1 times the change in voltage with respect to time, plus capacitance 2 times that change in voltage with respect to time. So again, we want to group terms together. So we go ahead and pull out that derivative, and we get the equivalent capacitance is equal to the sum of the two capacitances. So that's how you add up capacitors in parallel. And this is similar to resistors in series. Since we don't have an Ohm's law for capacitors, we just look back to the original format of the voltage-current relationship for capacitors, where we have a current equal to the capacitance times the change in voltage with respect to time. So now if we do the same thing for capacitors in series, we know that the current flowing through capacitor 1 has to be equal to the current flowing through capacitor 2 from Kirchhoff's current law. We know that the current flowing through capacitor 1 is equal to the capacitance, its capacitance, times the derivative of the voltage drop across it. And here the voltage drop across capacitor 1 is V minus V1. So we take the derivative of that with respect to time. And we can do the same thing for the current flowing through capacitor 2. So C2 times the derivative of the voltage drop across it. In this case, it's V1 minus ground. And since ground's our reference point, we say that's at voltage 0. So the voltage drop across capacitor 2 is just V1. So we take the derivative of that. So now we want to group the similar terms together. To do that, we need to break up that derivative of voltage 1 and voltage 2. So because it is a difference, we can say that the from our calc rules, we know that the derivative of a difference is equal to the difference of the derivative of each of the terms. So we can break that up to C1 times the derivative of the voltage with respect to time minus C2 times the derivative of voltage 1 with respect to time, and that's still equal to C2 times the derivative of V1 with respect to time. So now we'll get all those V1 terms on the same side, and then we can pull them out. So now we have C1 times the derivative of the overall voltage with respect to time is equal to the sum of C1 plus C2 times the derivative of voltage 1 with respect to time. So we want to group all those capacitances together. So we're going to solve for the derivative of voltage 1 with respect to time. So we just divide both sides by the sum of the two resistors, and we end up with this equation. But ultimately, we want to get back to that format where we have the voltage to current relationship for a capacitor. So to do that, we'll go back up to the beginning here. So we know the overall current flowing through the circuit is equal to the capacitance of capacitor 2 times dV1 dt. And we just solved for dV1 dt in terms of the overall voltage. So we can just go ahead and plug this term for dV1 dt, and we end up back at this format. So we can get the equivalent resistance or capacitance of two capacitors in series is just the product divided by the sum. So thinking back, capacitors in parallel add up like resistors in series, and capacitors in series add up like resistors in parallel. So if we want to think about the physical meaning of this, if we go back to that original equation where we have the capacitance is equal to the permeativity of the material between the plates times the area of the plates divided by the distance between them. If we add up two capacitors in parallel, it's like we're increasing the area of the plates. Since we're putting two plates right next to each other, if we bumped them right next to each other, it'd be like we had one really big plate. So having a bigger area increases the capacitance, and we know from the equation that if we add two capacitors in parallel, we're going to end up with a capacitance that's bigger than any of the individual capacitors in that circuit. Similarly, if we think about adding the capacitors in series, it's like we're increasing the distance between the plates. So if you even just look at the physical picture here, you can see that this plate is further away from this plate. So I like to think of it that way, just to build that physical intuition. And that means that the overall capacitance of this circuit is going to be smaller than any of the individual capacitors in that circuit. All right, so now let's put that into practice. So if we have this circuit where we have a bunch of resistors on this side being supplied by this power supply, and say we wanted to figure out how much current the power supply needed to provide, we could simplify the circuit by creating an equivalent resistor that represents the whole circuit. So to do that, first we can see that we have these two resistors in parallel, so we can group them together. So to do that, we just add them like resistors in parallel. So that gives us their equivalent resistance is just the product over the sum. And now we have two resistors in series. So we can go ahead and add those together, and that's a simple summation. So we add that first equivalent resistance we found for the two resistors in parallel to that third resistor to get the overall resistance of the circuit. So now we could just use Ohm's law to find the current that's flowing through this circuit if we wanted to. Another way of analyzing these circuits is using something that's known as the loop equations. The way these work is for every closed loop in a circuit, you say there's some current that's flowing through that. So here we can see we have this larger loop over here with I1 flowing through it. And on this side we have the smaller loop which has I2 flowing through it. So the way that this works is all of the current flowing through this loop flows through all of the elements in it, and all of the current flowing through this loop flows through all of the elements in it. But here at R1, we have one current flowing in this direction and another current flowing in this direction. So the net current flowing through R1 is the difference between those two. To think about this more intuitively, since Vn is in the same loop as I1, we know that all of the current for the circuit has to be equal to I1. So when I1 gets to the top of node 3, it has to split off. Some of it goes through R2, and that portion is I2. And because some of it is going through R2, that portion can't go through R1. So the amount going through R1 is I1 minus I2. So that's the way these equations work a little bit more intuitively. But let's look at the details of how you use the equations. This is a little bit ugly as it's drawn now, so let's go ahead and redraw that to make it a little bit prettier. Alright, so now that we have this drawn in a way that's a little bit easier for us to see the individual loops, we can start to analyze the circuit. So if we use Kirchhoff's voltage law, starting at node 3 for loop 2, we're going to come down and we cross resistor 2. So we have a voltage drop across resistor 2, which is equal to I2 times R2. We can see that in the equation over here. And then we continue along, get to node 2, and we come back up this leg, and we have another voltage drop. This one is equal to I2 times R1, since we're going in the direction of I2 to analyze this circuit. So we have that voltage drop, and we can see it here. But we also have this current from another loop flowing in the opposite direction of the way we're analyzing this loop. So instead of that being a voltage drop, that's going to end up being a voltage increase as we go around this loop. So we also have a voltage increase of I1 times R1, and then we've gotten back to our starting point. So we know that as we go around that loop, all of those values have to be equal to 0 because we need to get back to the same initial starting voltage for our loop. So if we use these to solve for the relationship between I1 and R1, we can go ahead and separate everything out. So we have all of the current terms separate, and then we can go ahead and group resistances. And then with one more step, we can get the currents isolated from one another. So then we have I2 equals I1 times R1 over R1 plus R2. So now we have the relationship between the two currents in the different loops. So now we can do the same analysis for loop 1. So if we start here at node 1, we have a voltage increase as we go across the power supply. So we can see that as V in here. And then we come around and we cross resistor 1. So we have a voltage drop which is equal to I1 times R1, which we can see in this term. We also have a voltage increase coming from the current in loop 2 going in the opposite direction through this resistor. So we can see that in this term here where we have a negative of a negative current. So this ends up being a positive value of I2 times R1. That brings us down here to node 2. We have one last voltage drop across R3, which is just equal to I1 times R3. So now let's go ahead and try and look at the overall current that's flowing through this circuit so we can compare it to what we've done previously. So if we go ahead and plug in the I2 I1 relationship that we had previously, we end up with this equation. And we can go ahead and pull out all of the I1 terms now and get all of the resistor values grouped together. So now we want to get this into a similar format to what we had before. So we'll go ahead and create a common denominator between the leftmost resistor term and the center resistor term. So that gives us this equation. And we can see here we have an R1 squared plus R1 times R2, which is the same as this R1 squared term. So we can go ahead and cancel those out. And that brings us to this equation where we have R1 times R2 over the sum of R1 and R2, all of that added to R3. So we want to get this in an Ohm's law form just to compare to what we've previously done. So if we bring the current and the resistor values to the right hand side, we've done that. And if you look back to what we did earlier, you can see that this is the same equivalent resistor equation that we found when we were analyzing the circuit before. So the two analyses should give you the same results, but why might we want to do the loop equations as opposed to equivalent resistances? One thing we talked about a little bit earlier is if you wanted to know the current flowing through individual elements, because you wanted to check to make sure you don't damage them. This is a good way of doing that, and you can look at each resistor and see which currents are flowing through it, and then just add and subtract the currents flowing through them as appropriate. Another reason you might want to do this is if you have a different type of element in the circuit. So here we have resistors and capacitors grouped together, and since a capacitor doesn't have resistance, we can't create an equivalent resistor for this circuit. We'll talk a little bit later when we're doing filtering about how you can handle this with impedances. It gets a little complex. That is a complex number pun, so it may not make sense now, but when we get to the filtering lecture and this comes up, I want all of you to laugh really loudly and say, "Oh, now I get it." All right, so now let's talk about voltage dividers. These are a really useful tool if you want to have a voltage at some part of your circuit that is smaller than what's being provided to the rest of the circuit. So one way of doing this is if you start with a resistor that's of a certain length and you cut it at some point and you put those two cut portions back together, you're not going to change the overall resistance of the circuit because the length of the two resistors together is going to be the same as that original length, but the resistance of each of the resistors is going to be dependent on where you cut that original material. So if you want to analyze how much current is flowing through the circuit, you can do that using the same equation we used before when we were looking at resistors being added in series. So you can use this to solve for the current flowing through the circuit. If you want to know what voltage is occurring at that central point, V1, you can analyze that as well. So you know that the voltage at this point is going to be equal to the voltage drop across resistor 2, which is just the current times the resistance of resistor 2. And from the equation above, we can solve for the current just being the overall voltage divided by the sum of the two resistors. And that gives us this equation here. So V equals R2 over R1 plus R2. So we can see that the voltage at point 1 is just equal to the percentage of R2 relative to the overall resistance of the circuit. So if we change that point where we cut the original resistor, we can change the voltage output. So there's a package that is designed to do this, and it's called a potentiometer. Essentially what it is a resistive material with a wire that you can slide up and down that resistive material, and you can use that to select what you want the relative portions of those two resistors to be. One thing to note when you're doing this is the voltage output assumes that the current flowing through resistor 1 is also flowing through resistor 2. If you're pulling current out at this point, less of the current is going to flow through resistor 2. So that can end up being problematic if that's a big percentage, or if that current is varying. A lot of times, if that current's constant, it's okay because you'll use these and manually set them. So if that's the case, it may not be that big a deal. But if that current that you're pulling out is fluctuating a lot, you may get large changes in voltage at V1. So if we look at what's on the inside of a potentiometer and how they work, you can see there's this resistive material that goes from one side to the other, and it's usually connected to the outer pins. So this is where you would apply your voltage. So we put the power supply on one side, so right here, and then on the other side we could put the ground or wherever the current is going to flow out of. The central pin is most likely connected to the wiper. So you can see here there's a wiper that you can move along that resistive material, and that essentially cuts it like we were talking about in the previous slide. And then this connects to that output pin. If we look at what a real one looks like, it's very similar to the picture we just saw. So we have the resistive material connected to the two outer pins. The central pin is connected to this big pad, and then connected to the knob or whatever you're moving will be the wiper. So here we can see this bigger wiper makes contact with the resistive material, and then the smaller wiper makes contact with this central pad. So that's how you get the voltage from some point on the resistive material out to that central pin. So that's the end of this video. Hopefully it's informative. If you need, you can go back through it and view it at your leisure.